Welcome to Decoding Causality, Season 1.
Great to be here.
This is our look at the 10th chapter of the Book of Why by Judea Pearl and Dana McKenzie. And it's actually our final chapter for this first season.
That's right, the end of this particular journey.
This podcast and the summary, by the way, were prepared by Amir Rafay. So today we're getting into some really meaty stuff where big data meets causality and even free will comes up.
Yeah, it's quite a finale. The chapter kicks off reflecting on a fundamental problem AI faced early on. Why was it so hard to teach machines about cause and effect?
Something that seems so basic to us.
Exactly. Especially given how good computers were becoming at other kinds of reasoning. It felt like an anomaly almost.
And it wasn't just AI folks scratching their heads, right? The book says scientists in lots of fields were asking causal questions, but felt limited.
Limited by sort of the standard statistical toolkit, which was really focused on association, on correlation, not necessarily causation itself.
Which led to this causal revolution.
Yeah, not like a single event, but more people from different areas. Philosophy, computer science, epidemiology, sociology, stats, all coming together.
What was the common thread?
Transparency, really. Being upfront about the assumptions you're making when you claim something causes something else, making the whole process clearer.
It sounds like a big shift. More confidence in talking about causes.
Definitely. A greater willingness to tackle those why questions head on. And the authors call this revolution the second gift of AI to humanity.
Okay, so that's the second gift.
Yeah.
What's the first?
Well, that's the big question they pose leading into the rest of the chapter. When will computers really get causal talk? When will they have that kind of, childlike imagination?
That ability to think, what if? That's a pretty deep question to end on.
It is. And it takes us straight into the topic of big data.
Right. I mean, the amount of data being generated now is just staggering.
Yep.
Facebook's data centers, the genome projects, NASA. It's almost impossible to comprehend.
Absolutely vast. But even with all that data, the questions we really care about are often causal, aren't they?
Like, does this gene cause cancer? Or what's making fish populations drop?
Exactly. Those are why questions.
And there's this tempting idea, isn't there, that if you just throw enough data and enough computing power at it, the answers will just emerge.
Yeah.
Data mining magic.
Yeah, that's a common misconception the book pushes back against hard.
Because
causal questions need causal models. You need a hypothesis, some understanding of the process behind the data. You can't just look at the data in isolation, model-free, and expect causal answers.
Okay, so data mining isn't useless, but it's not the whole story.
Not at all. It's incredibly valuable for spotting patterns, for finding interesting correlations. That's often the first step.
Like the example they use, finding a gene highly correlated with lung cancer, the Mr. Big gene.
Precisely. Finding Mr. Big is important. But then you need to ask why it's correlated. What's the mechanism? That requires moving beyond just the association.
You use the data mining result to formulate a causal question, then build a model to test it.
Exactly. But big data isn't just for that initial discovery phase. It's also crucial later on for the statistical estimation part.
Dealing with lots of variables, the curse of dimensionality.
Right. When you have many potential factors, you need a lot of data points to reliably estimate their effects and interactions. Big data, combined with modern machine learning, can help tackle that complexity.
Makes sense. Like in personalized medicine, maybe.
Perfect example. Causal thinking helps figure out which patient characteristics are truly relevant, which ones are just noise. And then big data provides enough examples of similar people to make tailored predictions or treatment recommendations.
Okay, now this next bit was really interesting. Transportability. Sounds like a fancy word for generalizing results.
It is, essentially. But it's about doing it rigorously. We have all these studies done in, say, California or New York or maybe a clinical trial setting. How do we know if those findings apply in Texas or to a different patient group?
That seems fundamental to science, applying findings more broadly.
It is. But actually creating systematic methods to figure out when and how you can do that transport is relatively new.
And this is where Elias Barenboim's work comes in.
Yes, working with Pearl. They developed criteria using causal diagrams, those visual maps of cause and effect, in the do calculus.
The do calculus. Remind me.
It's like a set of mathematical rules, a grammar for manipulating those causal diagrams. It lets you figure out if you can estimate the effect of an intervention, the do part, even if you can't run a perfect experiment. using observational data and the structure of your diagram.
Okay, so how does that help transport results?
Well, you represent the differences between the study setting and the target setting in the diagram. Maybe the age distribution is different, or income levels, or baseline health.
Like the surfboard ad example, selling surfboards online in LA versus Boston and wanting to know about Arkansas.
Exactly. LA and Boston populations differ in ways relevant to buying surfboards, age, maybe interest, online habits. You represent these differences graphically, often using a special variable that points to the factors that differ between settings.
So S captures the setting difference.
Right. And the do calculus then helps determine if you can still estimate the ad's effectiveness in Arkansas using the data from LA and Boston despite those differences.
It guides the computer.
Sort of. It tells you which studies are usable, whether you need to adjust or reweight the data from LA or Boston to match Arkansas, and maybe even what extra information you might need from Arkansas.
So it's not just a yes-no, it tells you how.
Sometimes, yeah. Sometimes it's a direct transport. Sometimes you reweight. And sometimes, interestingly, you might have two studies, neither of which is directly transportable on its own.
But together.
But by combining them in the right way, guided by the causal logic, you can get the answer for the target population. It's quite powerful, like data fusion.
Wow. Okay. And this also relates to selection bias, another classic problem.
It does. Selection bias is when the group you studied isn't representative of the group you want to talk about. Maybe only healthier people volunteer for a study, or only severe cases end up in a hospital database.
So the selection process itself introduces bias.
Exactly. It's similar to transportability, a difference between populations, but the structure in the causal diagram is often different. It's about factors influencing who gets into the study sample.
And the causal approach can help here too.
Potentially, yes. If you can model the selection mechanism, understand why certain people are in your sample and others aren't, you might be able to use causal inference in big data to adjust for that bias and recover an unbiased estimate for the population you actually care about.
That sounds huge. Because selection bias and external validity, generalizing results, these are constant headaches in research.
They absolutely are. And having formal tools to actually address them, not just point them out as limitations, is a really significant step forward. The authors are clearly excited about it.
You can feel that enthusiasm. Okay, so from the practicalities of data and transportability, the chapter then pivots quite dramatically.
It does, towards strong AI, artificial general intelligence, and even free will. Big philosophical territory.
Yeah, it revisits that initial AI question. Are we getting closer to machines that understand causal conversations, that have imagination?
And it looks back at older AI approaches, rule-based systems, expert systems. They were often brittle, couldn't handle unexpected situations well.
Lacked common sense, basically.
Pretty much. Then came Bayesian networks, which were a big improvement. They handled uncertainty probabilistically, much more robust.
But still not causal?
Not inherently.
Yeah.
A Bayesian net tells you about dependencies. If A and B are linked, knowing A changes your belief about B and vice versa. It doesn't automatically tell you if A causes B or B causes A, or if there's common cause C. That asymmetry is missing.
And that missing piece is what really pushed Pearl towards causality.
That's the story, yes. The need for AI to understand not just correlation, but causation.
Then came the deep learning revolution, neural networks. AlphaGo beating Go champions. Amazing stuff.
Truly impressive feats, but often described as opaque, right? Black boxes.
We don't really know how they do what they do.
Even the programmers might not fully grasp the internal logic. And critically, while they excel at pattern recognition, seeing complex associations, rung one of the ladder of causation, they don't inherently grasp cause and effect.
Well, they see correlations, maybe very complex ones, but not the underlying forces.
Exactly. And for strong AI, for machines we can truly communicate with, that understanding seems essential.
They need to understand counterfactuals, the what-ifs.
Think about trying to explain, you shouldn't have woken me up to a robot.
Okay.
It needs to understand action, making noise, affecting, consequence, I'm grumpy. And the counterfactual, if you hadn't made noise, I wouldn't be grumpy. That requires causal reasoning.
Current deep learning struggles with that. Reasoning about untried actions or hypotheticals.
That's a key limitation highlighted in the chapter. It's a major hurdle for strong AI.
And this leads into the idea of intent.
Yes. Our own decision-making feels driven by intention. We consider options, we choose. And the idea of a machine considering its own intentions, maybe choosing differently, well, that starts to sound a lot like free will.
Ah, the philosophical minefield. Free will versus determinism.
Right. The feeling we have choices versus the idea that everything is predetermined by prior causes. The chapter mentions the compatibilist view,
which suggests
that maybe it's not a direct clash. Maybe free will and determinism are descriptions at different levels, like the neurochemistry might be deterministic, but our conscious experience operates with a sense of agency and choice.
So the focus shifts to the function of free will. Why do we have this feeling, this illusion perhaps? What's the benefit?
That's the key question. The book suggests this illusion is incredibly useful. It lets us talk about intentions, reason about them, apply counterfactual logic.
Like the coach saying, you should have passed.
Exactly. That's not just a critique. It's packing complex causal reasoning into a simple instruction. It's asking the player to mentally simulate the alternative action passing and its likely better outcome. It operates at the level of intent.
It's a powerful shorthand for causal instruction.
A very efficient one. And the suggestion is maybe even robots would collaborate better if they operated as if they had free will, reasoning about their intentions.
And certainly for us to interact naturally with them, they'd need to understand our talk about choices, intentions, regrets.
They'd need to grasp that vocabulary, emulate that process. This reasoning about one's own beliefs and intentions is core to the idea of agency.
Agency, like being an actor in the world, not just reacting.
Right. And the algorithmization of counterfactuals is seen as a step towards making agency computationally achievable.
So what would a machine with agency look like internally?
Maybe a causal model of the world, plus a causal model of its own software, even a simplified one, and a memory linking its chosen intentions to observed outcomes, learning from its own simulated or real actions.
Interesting. Almost like learning responsibility.
Which naturally leads to the concerns. If we build machines with agency, what about the risks? People like Elon Musk, Stephen Hawking raised alarms.
Understandably. The chapter mentions John Brockman's edge question. What do you think about machines that think? Captures that anxiety.
Yeah, and it tries to unpack that anxiety with those 5 questions. 1, have we made thinking machines? Answer, no, not human-like.
2, can we?
That's true.
Almost certainly yes, defined by mastering all 3 rungs of causation.
3, will we? Answer, likely, but ethical debates are needed. 4, should we? Answer, yes, link to the next question.
Which is 5, can we make machines that know good from evil? Answer, yes, potentially as reliably as humans or even better.
And the key here, again, is counterfactuals. The ability to reflect what if I had done otherwise is seen as fundamental to moral reasoning.
So morality isn't just rules, it's about understanding consequences, reflecting on actions.
Exactly. It suggests you could build self-awareness, empathy, fairness on these computational principles. It's very different from Asimov's laws of robotics.
Those rigid rules that always seem to lead to paradoxes.
Right. Instead, you equip the machine with cognitive abilities, empathy, or an analog, foresight, self-reflection, and let it learn and make decisions based on causal understanding.
The potential being, they might even be better at ethical reasoning than us sometimes. Less biased, maybe.
That's the provocative suggestion. And such a machine with agency and a moral compass built on causal reasoning wouldn't be a threat, but potentially.
The first and best gift.
Absolutely. The models are key. And thinking about strong AI through this causal lens, it really changes the conversation, doesn't it? Away from just pattern matching towards genuine understanding.
Yeah. The idea that free will might have this functional, computational aspect related to counterfactuals is, well, it's a lot to chew on.
It definitely is.
So as we wrap up season 1, what parts of this discussion really stood out for you, our listeners? Are you leaning more optimistic or cautious about AI gaining this causal understanding? And what about programming machines with agency, maybe even that illusion of free will?
Lots to think about.
We really encourage you to keep exploring these ideas, maybe dig into Pearl's work further. Thank you so much for joining us throughout this first season of Decoding Causality. It's been a fantastic journey into causal reasoning.
We look forward to more explorations in the future.